So these are Newton's laws. Let's read it carefully. The first law: objects at rest remain at rest, and objects in motion remain in motion in a straight line unless acted upon by an unbalanced force. Right. So there's a few words that we might want to highlight, so as we know what's going on there. First of all, rest. That means not moving, right? So anything sitting still will keep sitting still. And anything in motion, so let's pick a different color. In a straight line, yes, in a straight line is important. Well, remains in, so they remain in a straight line. Moving at. Hang on a second. Let's just have a look at this. Remain at rest, and objects with motion remain in motion in a straight line. So, yes, okay, all right. Well, there's other things later on that which we need to bring into line with the first law. So usually when I end up teaching this, I'll end up mixing the laws together a little bit, but that's fine. So as long as we, so let's think of an example. We've got a ball sitting on the floor. If nothing happens to it, then it carries on just sitting there, right? So that's Newton's first law. If I apply a force, if I push it that way, but friction opposes it, then the resultant force is zero. So F total is zero. That's why it says an unbalanced force, okay? So, but once I've opposed friction and the resultant force is greater than zero, then it no longer stays at rest. It starts to move. Now, the next bit, if it's already moving, so let's imagine a meteor flying through space. I'm going to use an arrow like this underneath it if I'm labeling velocity. So velocity, it's moving through space, but if there's no force on it in this situation, no force acting on it, the force total is zero. In this situation, it carries on going in a straight line at that speed. Now, we came across this use of Newton's first law when we looked at terminal velocity, because in terminal velocity, we did have a force going one way. In that case, it was going down, but it could be going any direction. But the resistive force, in that case, was air resistance, was cancelling out. It didn't stop like in our first case. It just didn't accelerate, and it didn't slow down. It didn't decelerate. So Newton's first law is saying that it could, if there's no resultant force, it's not going to speed up and it's not going to slow down. It's not going to change direction either. It's going to continue to go at that speed in a straight line. Now, this is what's not explained within it, that the acceleration is zero. But that comes into play when we look at the second law, which we'll come to in just a moment. But just a little bit more on the first law. Let's think about an object that is moving in a circle. So this is the moon going around our Earth. We'll label that E for Earth, M for moon. It's not speeding up, but it's still a force acting upon it because it's not going in a straight line. And we can also refer to this from our other things that we've thought about, the fact that the velocity is not staying the same because velocity has a direction and the direction is changing, so therefore the velocity is changing. If the velocity is changing, there must be a force acting upon it. Or we could say if the velocity is changing, it must be accelerating. That's a bit weirder, but we'll come back to that another time. But in any case, there is a force acting upon it because it's not going in a straight line. The force is gravity, and it's acting towards the Earth. Okay, so that's the first law. So if something is sitting still and there's no forces acting upon it, it stays sitting still, or if there's no resultant force. If something is moving and there's no resulting force acting upon it, it continues to move at that speed in a straight line. So if it's either speeding up or changing direction or slowing down, a force must be acting upon it. Okay? If it's speeding up, slowing down, or changing direction, there must be some force acting upon it. And it's often our job to work out what is that force. Okay? Right. So second law tells us how we can go about working out that force. If we come back to one of these situations, let's say we've got an object and yes, it's moving, it's not moving at constant velocity, but it's accelerating. If we knew what acceleration was and we knew what the mass was, we could actually work out what the force must be using this equation here. F is equal to ma. Okay, you can rethink about this, and maybe a better way to think about this question is by rearranging it. Acceleration is equal to force divided by mass. This version of the equation basically says that the acceleration an object would feel would be equal to the force applied to it divided by its mass. So I can apply a large force, but if I'm pushing a very heavy object, it's going to accelerate at a lower rate. It's going to take longer to speed up. Whereas if it's a lighter object, I can make it speed up very, very quickly. I can get it to a high speed very quickly. So that's Newton's second law. Now, by the way, all these laws you come across in GCSE as well. But the difference with the second law is that the second law, we think of it in a slightly different way. Eventually, we're going to come across this use of the word momentum, which we haven't done yet, but it will come up. Yeah. So in a nutshell, momentum is how difficult it is to stop something. That's a nice way to think about it. It's not really officially described as that, or it sometimes is referred to in that way, but if something has a lot of momentum, it's difficult to stop it, or it's difficult to slow it down. Yeah, difficult to stop it is fine. So it's actually equal to the mass of the object multiplied by its velocity. So if it's moving faster or if it's heavier, it's difficult to stop it. Okay. Now, when at GCSE, you learn that the force is equal to mass times acceleration. At A level, we tend to learn that the force is equal to the change in momentum. Sorry, I think I just said that last sentence wrong. At GCSE, you learn that the force is equal to the mass times the acceleration. At A level, we learn that the force is equal to the change in momentum divided by the change in time. So how is that the same as this? Well, it's the same because if we imagine that the mass stays the same, which it almost always does, but not always, but almost always. Incidentally, one of the times it doesn't stay the same is with rocket science, but we're not going to look at that yet. So the mass would stay the same. So we can take the mass outside of the change because it doesn't change. So we can say mass times the change in velocity divided by the change in time. Change in velocity divided by the change in time is acceleration. That's what acceleration is. All right, it's the rate of change of velocity. So therefore, that is the same as mass times acceleration. Okay, so it's fine to really think about it in this way, but eventually you'll be thinking about it in this way. They're both Newton's second law. Originally, Newton said that the force is equal to the rate of change of momentum. He didn't say, he may have said this as well, but he phrased it in that way. The force is equal to the rate of change of momentum. And at GCSE, we teach it like this, because it's a bit easier. Newton's third law says for every action, there is an equal and opposite reaction. If we go, let's go to some of the examples I've looked at so far. This object sitting on the table, it's not moving, but it does have a weight, and that's going to be acting down. It doesn't move down, however, because the force is applying a force up. That is equal and opposite. Okay? If we look at this example. Oh, sorry, go on. It doesn't, the ball or the rock or whatever it is doesn't move down because the table it's sitting on is applying a force upwards. And if there wasn't a table and it was in the air, then of course it would move down. But if it's on a table, we often think, when I'm teaching this at GCSE, I say, why isn't the thing just moving down? We know it's got a weight. We know it's gravity is pulling it down. Why isn't it moving down? My students just look at me like I'm crazy and say, well, because the table's in the way. And I say, that's correct, but I need to know an answer in terms of forces. We know that forces cause action, forces cause things to move. So there must be a force pushing it up. Otherwise, it would be moving down. And then the answer is the table applies a force in the equal and opposite direction. Now, a way to think about this is that if you press your finger down on the table really hard and you look at your finger and you sort of feel like, my finger's kind of hurting now. Well, what was it that was pushing on your finger? It was the table. The table was pushing back on your finger. So you pushed the table, but likewise the table pushed your finger. And that's why your finger didn't go through the table. Didn't keep going down. It's kind of, there is a little bit of a, it doesn't completely answer the question, but it's halfway there. It's a good way to think about it anyway. We look at these. There are some other examples of Newton's third law, though, like this one here. We were talking earlier on about how the moon must be attracted towards the Earth, and we've got this force here. Well, actually, a lot of people don't realize that the Earth is also, or they don't think about it, the Earth's being attracted to the moon too. And the size of the force that the Earth feels towards the moon is the same as the size of the force that the moon feels towards the Earth. And that one really confuses some people. So let's just draw that out again. So if I apply a huge, imagine a great big massive planet like this, and then a smaller planet like this, and I'll just move that. I'll try to move that up if I can. Yeah. So that this great big planet here is going to be attracting that planet there, but this is also attracting that great big thing there with the same size force. So first of all, clearly that's going to cause people to think, huh? But from that, huh, you've got to be able to think, what is it that doesn't seem to make sense about this situation? The reason why this doesn't seem to make sense is because if I lift up a book and let go and it falls towards the earth, am I saying that the earth jumps up and meets the book halfway? No, I'm not saying that. And so why doesn't that happen? How can both those things not be true? Well, the reason is because of Newton's second law, which was F is equal to ma. In both cases, they both feel force F, but in this case, we've got a big mass. In this case, we've got a little mass. So on the one on the left, the acceleration 1, this acceleration of the big planet, is equal to the force divided by a big mass. So a very, 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 very small acceleration because it's divided by a very, 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 very large mass. In this case, the acceleration is equal to the same size force divided by a very, very small mass. So acceleration of the tiny object is going to be much, much larger than the acceleration of a very large object. So it is true that when I lift a pencil up and let go, the earth accelerates towards the pencil. But the acceleration is so ridiculously tiny that you may as well forget about it. In fact, you can forget about it because there are other people all around the planet potentially dropping pencils and or dropping other things, and they're also applying a force on the Earth, and so overall it's going to cancel out anyway. So, but if there was only one person on the planet and that one person dropped a pencil, the Earth would move towards the pencil and the pencil would move towards the Earth, but the Earth would move, the acceleration of the Earth would be really, really, really tiny, and you could pretty much forget about it. Okay. However, the force is the same. Okay.